All right, let's see if the audio is on. Okay. All right, everybody. So on my website, if I go back there, if I find it, here we go. Worksheets and videos. Looking for optimization. What do I have here? Okay, that's a nice line. Square root. Okay. And what's the point over here? All right, 3-0. So I do have some optimization questions. I don't want to do the ones I have there necessarily. So I'm going to create some additional ones for you. And if I said to you guys optimization, that is something, what should I say? Here's really what this is based on. Optimization is code for relative max, relative min questions. So they're essentially relative max, relative min questions. But yes, you're trying to optimize a physical phenomena. And I'll show you what I mean. For example, the first kind of most popular question they give you, there's a lot of different kind of popular questions. They might say, find the point on the parabola. Share with you guys an optimization. Y squared equals 2x. That is, quote unquote, closest to a point that's off the curve. 1, 4. Okay. So let me give you guys the idea behind optimization. You're really going to find a function. You're going to create a function, f of x, where you're really going to find the relative max or relative min. So you create that function, you're going to find either a relative max or relative min. That's what they mean by optimization. You'll see what I mean by that example. Let me make sure I make this kind of clear for you. Y squared is 2x. Believe it or not, that's a parabola. So I'm going to go to Desmos here, okay? So that's for the trig class. Y squared is 4x. So here's our graph. And I think they have a 0.14. And let's label that blue as well. Okay, so here's the parabola. I'm going to bring this in. Excuse me? Did I put 2x? Okay, thank you. Did I put 2x? All right. All right. So let's get another picture. Thank you. And let's bring this in. Next, I'll bring it in like this. Add to existing note. So there's going to be a lot of different kind of, well, not a lot, but I mean, there can be a lot. Of course, we can't go over every kind of optimization you can see in your life, but we could do some of them. Now, let's kind of read through what they're trying to get us to do, right? They're saying find the point on the parabola. Okay, so there's going to be a point on the parabola. And here's the curve. Here's the parabola. This is a parabola from Math 260 pre-calculus, if you guys remember. And then there's a point, an x and y coordinate. They're saying, hey, at what location, if I just do something like this, there's a point on the curve. Here's various points on the curve. Okay? And then you have a distance here. Distance D. These are all distances. And you say, okay, what do they mean by this? Find the point on the curve, the xy coordinates. Okay, so here's kind of an arbitrary point on the curve. They want to say find a point That's what they mean by that. That is what? Closest to this point out in space, 1, 4. Okay? So I just want to kind of share this idea with you guys. The closest point is one with the shortest distance. Does that make some sense? And so really, ultimately, you say, what is optimization? Well, you're going to create some function f and then find relative max, relative min. It's either going to have a max or a min. It's not going to have both. So in this case, what's really going to happen is you're going to create this d of, you're going to find this d of x. Right? They really mean d, which is d of x. It's the distance formula. So you're going to use the distance formula here because that's a fundamental measure in geometry, right? The distance formula. Do you guys remember that distance formula? Very, very important formula in geometry. Okay, it's a fundamental formula, distance formula. So we're going to use the distance formula. And now you might say the distance between what? Well, a point on the curve and 1, 4. So you can think of that as, for example, here's a point on the curve, your first point, maybe your second point. Okay, 1, 4, and then an arbitrary point on the curve. So you might say, what was the distance formula? Do you guys remember the distance formula from geometry? D is really what? It's a variation of the Pythagorean theorem. X2 minus x1 squared plus what? Y2 minus y1 squared, if you guys remember that one. It's your distance formula. Now that's the distance between 2 points on any curve. So if I plug in the values, right, you say, what do you mean? Then your distance formula really becomes the following, that D will be x minus 1 squared plus y minus what? 4 squared, I believe. Okay? So you might say, where does that all come from? Right here. Okay, this is for 1, 4, this is the x coordinate and the y coordinate. So you have x1 is 1 and y1 is 4, where x2 is x, y2 is just y there. That's your distance formula here. Okay, and then you might say, all right, well, what do we do with this now, right? So D is a distance formula. That's going to be your function. But the problem is you have two variables, right? You have the x variable and you have the what? Y variable. We want to use only one variable. Okay, so this is already, just so you guys could know the details here, is that this function that you're seeing here is really a function of two letters, x and y. We need a single variable. This is calculus of a single variable here. So then you might say, well, what do I do here? Well, I think this equation here, y squared is 2x, right? Since y squared is 2x, I can actually solve for x easily, where x will be y squared over what? 2. So what that now does for this distance formula is I can now say, well, is this y squared over 2 minus 1 squared plus y minus 4 in parentheses squared square root. So now my distance formula here is in terms of the single variable y. So this is calculus of only one variable. Up here, you'd have two variables for the distance formula. You need an x and y coordinate. So I'm also going to do just a little bit of, well, I'm going to do this. If I square both sides, what you end up getting by squaring both sides, this is a classic demonstration, is you get 1/2 y minus 1 squared, okay, plus y minus 4 squared, and that's now d squared. We're going to let this be, ladies and gentlemen, your function. D squared is really the function. This is a function of only one variable. So you want to write this in terms of one variable. So here's what I'm saying, really. You got this function d squared, or you have f of y is 1/2 y minus 1 squared plus y minus 4 squared. Okay? So this is really the function you're looking for. And what we say with this function, you're going to really want to optimize that function. Okay? They very often say, hey, optimize this function. All right, what does that mean? If we're going to find this is called optimization, right? How do you optimize the function? All they're saying is, what's the relative max or relative min? It's going to have one, a relative max or relative min. In this case, it'll be a relative min, and I'll show you guys why. You say, why? Because they're asking for the shortest distance, d, even though that's now d squared. You say, why do we use the d squared? Because it makes the calculus easier. Okay? It's easier to do derivatives when you don't have that square root. So now the calculus is nice and easy. And that's kind of the little trick that you guys use for using that distance formula to get rid of the radical. They use that little trick, squaring both sides. So yes, you do have the square root, but square both sides, and now that function's really d squared. Everything's still going to work out. So then now you say, well, how do I use calculus? You guys know. You just had a test on this. What do you guys do? You have to differentiate. Is that right? And after you differentiate, what do you do after that? Anybody know? What happened to my notes? What do you do after you differentiate? Well, let's differentiate. So this is the optimization part, right? So f prime y is going to be what? You're going to differentiate with respect to y, because that's the variable. You got 1/2 y minus 1 squared plus y minus what? 4 squared. So you're going to have to use some derivative skills. What do I mean by derivative skills? Anybody know? What am I really talking about? Yes, derivative of a sum is sum of derivatives. What do you guys use here? Do you guys know? Anybody have an idea? What are you guys going to use here when you differentiate? Good. You're going to use chain rule. Good. Chain rule. So this becomes, if I move this down here by chain rule, right, you're going to get now what? 2 1/2 y minus 1 times 1/2. Is that true by chain rule? Plus 2 y minus 4 times 1 by chain rule. So don't forget your chain rule. And now you get 1/2 y minus 1 plus 2y minus what? 8. Is that true? Double check my arithmetic. I haven't had my second cup of coffee. And so I'm thinking it looks like it's okay. Let's see, 2y minus 4. All right. So 2y and 1/2 y. Isn't that going to give us what? Is that 5/2 y Minus 9. All right. Double check, ladies and gentlemen. Double check our calculus is okay. Yeah, it looks okay to me. Okay. So what do you do with this derivative? Right? You're going to set that equal to 0. We're finding relative max, relative min. So you get 5y, 5xy minus 9 is 0. Now, I'm going to use blue. Which means 5 halves equals 9, or y will be 9 times 2 fifths. Is that right? So our y value will be 18 fifths. Okay, this is a critical what? Value. You need to find the relative max, relative min. This is what optimization is. So what do I mean by that? Do you guys know what I mean? What are we using here? Sign what? Analysis. So that's the critical value on the first derivative. These are y values. Notice that's 18 over 5 on that first derivative. That's where it's 0. So I have 2 quadrants, one to the left and one to the right. So when I'm going to use as test points, I like 0. It's available. And then 18 fifths, isn't that? I think 4 is available. Is that true? As a test point. And I got to use that on the first derivative. So I'm going to go back and say, what was the first derivative? Here we go. The first test point, if I plug in 0, oops, sorry. No, that's not the first derivative. Where's our first derivative? What's f prime of y? Here it is. So what happens if I plug in the test point of 0 here? Do you guys know? Is that negative? It's negative. Is that right? So negative. So that means region 1 is decreasing. Okay, now let's plug in 4 for that test point. So 5 halves times 4, isn't that going to be 10 minus 1? 10 minus 9, sorry, is 1. And that 1 is positive. Okay, so ladies and gentlemen, take a look here. That is going to be increasing. What does that mean is happening right here at 18 fifths? This is a relative what? You have a relative min. So ladies and gentlemen, this is the value of y for which you have a what? A relative min value. A relative minimum value for what? For your function. 18 fifths for y. So it's a relative min for this function right here, f of y. So then you say, well, what in the world does that mean? This is a relative min. So, okay. Let's write down what this means. So you get a relative minimum value equals to f of what? 18 fifths. This is that y coordinate. So notice what the question, though, is. Okay, here's the question. They want to know what's the location, the y coordinate. Get rid of all these. What's the y coordinate here? Get rid of that. On your curve. 18 fifths. What is that? Isn't that like 3 and what? This y value, isn't that 3 and 3 fifths? right? I think so. 3.6 or so. Anyway, it looks like it's 3.6. Well, what's the x coordinate going to be? How do we get the x coordinate? Right? I think we have the y coordinate, don't we? How do we get the x coordinate? What is x? Go back up here. What's y squared? Isn't that 2x? So if your y squared is 2x, what happens when we plug in that y value? Right? This will be 18 what? Fifths. So that means x will be y squared over 2, or 18 fifths squared divided by 2 for your x coordinate. What is that? What is that going to be? 18 squared over 25 divided by 2. So x will be 18 squared over, it looks like 50, right? So anybody know what 18 squared will be? $324. Now they're both divisible by 2. Is that right? So what does that mean? 162? So x will be 162 over 25, I guess. I think that's pretty much it. So you're going to have these two coordinates, right? An x coordinate and a what? Y coordinate. So here's the location. The x coordinate, 162 over what? 25. And then what's the y coordinate? 18 fifths. Let's go back and take a look. And then something's okay. X, this looks like x is what? X is 1, y is what? 4. Okay. So x is 1, y is 4. We look like we're okay. I want to take a look at this numerically just so you guys can see. 162 divided by what? 25 is about what? 6.48. And y is at 18 divided by what? 5? Oops. Three 6.48, 3.6. Six point four eight, 6.48, 3.6. Something's bothering me about this. It's odd. Let me double check if this is on the curve. Where is that? 64836. It's a little odd to me. Shortest distance? Doesn't look like that would be the shortest distance. Yes.
How'd you get the y without it being y squared? Like for the.
Yeah, something's bothering me about that. See this point on the curve? Alrighty, let's go back here. All right, double check here. Y squared is 2x. Yeah, we did put that. Y squared is 2x. Okay. And it is a point on the curve, so something's not right. Okay, what's your question?
Right there.
Where?
In the f of y.
Right here.
Yeah. How'd you get the y without it being y squared? Is that?
Well, there you go. That's where the error is. Thank you so much. Thank you. That's why. Okay. Apologize to you guys. All right, that's going to change everything. All righty. So I think probably that's why there's an issue. Whatever. All right, let me do this here, okay? I'm going to have to do this. That's why it made no sense. Did you guys see why it makes no sense? Let's go back to the picture in Desmos. That's why. Thank you so much for catching it. That's why it makes no sense whatsoever. Just tells you there's an issue. Look at all that work. Couldn't you find the error way before? All right. Let's find this error here. And I was like, wait a minute. It doesn't make sense. That means there's a problem. All right. So, you know what's kind of weird is that that point still was on the curve. That's kind of odd. Anyway, let me go back here, right? Here's my point to you. Do you see why this doesn't make any sense? Why didn't that make sense? That point on the curve, it's still on the curve. That's the closest point? No, the closest point would be somewhere over here. Do you guys know what I'm saying? The closest point should be somewhere like maybe even there. Let me prove that to you guys. That's why it made no sense. Okay, I guess we have to go back and, all right. Everything. All right, so here we go. Now this is going to be two, sorry. Okay, by chain rule, what do you guys get? Isn't that just going to be y? Plus 2 y minus 4. Okay? Is that true? Double check. 2, 1/2 y squared minus 1 times 2 times 1/2 y, which is just y. So 2y, 1/2 y squared minus 1 plus 2y minus 8. Okay. Which is going to be, if I distribute, is that just y cubed minus 2y plus 2y minus 8? And then that gives you a y cubed minus what? 8. Double check, ladies and gentlemen. I have not had that second cup. Is that right? Double check my arithmetic. It looks good. Y cubed minus 2y plus 2y minus 8. And that's kind of nice. You guys know why that's nice? Optimizing sign analysis. Find the what? Relative max, relative min. Okay. So that means y cubed minus 8 equals 0. This is kind of very nice. Y cubed equals 8. What does that mean about y? Y equals 2. This is my what? Critical value. So it looks like it's even nicer than we can imagine. So at 2, the first derivative is 0. Region 1, region 2. Okay, get your test points. Maybe a 4, I don't know. Plug in a 0, it's negative, is that right? Plug in the 4, it's positive. Okay, it's the same exact situation. And ladies and gentlemen, you have the same thing. But where's your relative min at?
2.
At 2. So the relative min is really f of 2, but this is the y coordinate here. Okay. So what was the relationship again? We need the x coordinate. Okay, so the x coordinate is going to be, where is that again, ladies and gentlemen? Y squared is 2 over x. So y squared is 2 over x, or x will be y squared over 2. Plug in the 2. 2 squared over 2, x will be what? 2. So here's the point on the curve. X is 2, y is 2. Right? All right. And I think in Desmos, I can't remember if that's a purple curve, but all right, let's do this here. So x is 2, y is 2. Okay. Let's go back and see if that makes sense. It was purple. All right, come on. 2, 2. And sure enough, ladies and gentlemen, that makes more sense. Okay, so you say, what do you mean it makes more sense? Does it make more sense at that location, 2, 2? Should be the closest point to 1, 4. Remember, the point they're talking about has to be on the curve. So that makes a lot more sense to me. In fact, there's another way of doing this. I won't go through that, but you find the derivative. Anyway, normal line. Let me say this. Your normal line at 2 should be perpendicular to the tangent line at 2, I think. Anyway, I won't go there. But that makes a lot more sense, 2, 2. Okay, thank you so much for catching that error. But this is a classic question of always finding a point to any curve that is closest to another point, any point in space. And so there's a few examples in your book on that. You optimize, and then should we go to, how about this other classic kind of questions? I'm just going to give you some classic questions, okay? Some classic examples here. Fundamental classic examples. Okay, let's see. Here's another example. All rectangles they say, with your book says, with a given perimeter, okay, whatever that means. I'll express that to you guys, what this means. The one, they're talking rectangle. It's really not a rectangle. With the greatest area. okay, is a square. You might say, what are they even talking about? Well, if you had to create a perimeter, a rectangular perimeter, and you want the maximum area, the biggest area, right? You're not really creating a rectangle. Here's what they're talking about. So remember, you have this rectangle with the length and the width. What's the perimeter formula? Isn't it 2L plus 2W? Okay? And ideally, what they want you to know or to show is really going to be the following. You know, what dimensions give you the maximum area? So they're really asking you that kind of question. Generally speaking, what dimensions will give a maximum area? Okay, this is kind of what they're really saying here. So when they say dimensions, they want to know what's your length, what's your width, generally speaking, that gives you a maximum area. It's kind of like if you have fence and property, you want to enclose the maximum area. All they're going to say, you know, notice this, they say, oh, you have to make a square. All right, well, we don't know that, but that's what the statement is. That's the general statement. So they can give you any sort of dimensions for a perimeter. They can say, hey, if you got 500 feet of fence, you know, what dimensions will give you the maximum area? This is really kind of the same question. They want you to learn that it's really not a rectangle. It has to be a square. You go, what do you mean? How do we know that, right? Well, let's find the maximum area. What's the maximum area for a rectangle? Do you guys know? Or I should say, what's the area formula? Isn't that length times width? So we're going to have to create this function and maximize it or optimize it. So you might say, well, how do they begin to do that? Well, you have to take this perimeter here, right? You say, what do I have to do? I got to actually, what? How do we write this area formula in terms of one variable, right? Your area, what's your area? It's based on two variables, L and W. But you really can't do that because they didn't give you some fence, right? So here's kind of, we can do it in general like they have here, or I can even give you just a fixed amount of fence so that you guys can say, oh, okay, I see your point. So if they gave you, I'm going to give you guys a note here. 100 feet of fence. So your perimeter is going to have to measure what? 100 feet. So here's kind of how they really could give this to you, I guess. You can say, well, 100 is 2L plus 2W. And you're still going to have the same issues. If you're going to maximize the area, how do we optimize this area function? Right? It's two variables. You have to write it as a single variable. So then the question is, well, how do you do that? Well, pick a variable. Which one do you want? L or W? Maybe you say, I want L. Okay. So you want to write this in terms of a single variable like L here. And to do that, or W, it doesn't matter, right? Solve for one of the variables. If you solve for W, 100 minus 2L will be what? 2W, or W will simply be what? I won't do the arithmetic yet. 100 minus 2L divided by 2. So your W is going to be 50 minus L. Okay, that's W. So here's my point again. To find that area formula to show that it's going to be a square, L and W is 50 minus L. So you solve for W here. So now your area formula is 50L minus what? L squared. Okay? So this is now a single variable, meaning A of L. And you say, how do I maximize this? Well, you're going to have to use calculus. You have to find the relative what? Max, relative min. This is the idea behind what? Optimizing, really. They should really just say, hey, find the relative max, relative min of a function here. That's all it is, but they call it optimization. It's either going to have a max or a min. The last example had a min. This is going to have a max. And notice something here. This goes back to like, I don't know, intermediate algebra maybe? This is a parabola. It's an upside down parabola. If you guys know. Is that right? Upside down parabola? All right. Well, you have to use calculus. So in other words, we have to find A prime of L. So we differentiate the function with respect to L. This is optimization. So the derivative becomes what? 50 minus what? 2L? Is that right? So sign analysis, set that equal to 0, and your 50 minus 2L gives you what? That equals 0. That means 2L is 50, or L is what? 25. So the length of that rectangle is 25. What would the width be? Do you guys know the width? You go back in for W and plug that in, and you're now going to get for W what? 50 minus 25, and then W will be 50. So the moral of the story is, from the statement they gave you, another classic example, is that the rectangle you have to always make isn't, in fact, a rectangle. It depends on what you mean. It's really a special case. It's a square. They have to have equal what? Dimensions. It has to be 25 by what? Oops. Yeah, 25 by 25. I made an error in my arithmetic. I got to get some coffee. Up at 4 a.m. working. 25 by what? 25. So here's the point of the statement that, at least in my notes, so always share with the class that if you're ever going to maximize the area, right, meaning everything in here, you can't create a rectangle. It has to be a square. Okay, you'll have to have a square always. It doesn't even matter. I can even prove it in general, but I could just show with you guys this, something like this. But this is another very classic demonstration of optimization in a calculus course, right? Closest point on a curve to another point off the curve. That's one classic demonstration. Another one is finding showing the class that there's no way you can create a what? A rectangle. I mean, you can create a rectangle. They all have areas. But if you want to maximize the area, finding a max has to be a square. There's no way around it. And, that's another classic demonstration of optimization. There's a lot I can do. Should we show you another classic demonstration? These are all classic questions in the world of optimization. Here's another one. They're going to give you, like if they said to you, there's 1,200. This is volume. Okay? They're going to give you a volume of material is used to make a box. with a square base. And an open top. Means there's no top. Find the largest volume of the box. What are they talking about? I gotta check the book, see if I'm phrasing it. I don't want to phrase it incorrectly. Optimization. Okay, here we go. Find the. Oh, nope, it's a different book. Sorry. Different book. I do that sometimes. All right, let's figure out what they're talking about. Well, you got some material, and to make a box with a square base. So let's write this down here, okay? My pictures aren't going to be the best. Something like this. Okay. Maybe something like that. And a square base. So that's S and S, okay? So this is a rectangular box. Now this here, this is units. I should say to you guys, this is volume, by the way. This is V for volume. So this should say a volume of material here. Okay. And my box isn't that straight, but I can straighten it out. Okay, so what do we know? There's no top. So there's no top. There's only sides, no top. So what I want you guys to know is this. What's the volume of a box? Isn't it length times width times height? And in this case, you have height, but in this case, the length and width are the same. So this is S squared what? H. You guys with me on that? And do you guys know the surface area is really 2L, well, let's be careful. 2LW plus 2LH plus 2WH, okay? That's in general. And maybe I should just do this to say to you, here's going to be maybe our length, our width, and our what? And our height. And they said, oh, the base is square. Okay. So maybe that helps us. L is S and W is S. So L is S, W is S, L is S, W is S. So my surface area formula in this case is 2S squared plus 2SH plus another 2SH, it looks like. All right. So the surface area is going to be the 2s squared plus 4sh. So I want you guys to know, so these are like the key equations here, that they're giving you a volume of material to make a box with a square base, open top. I think it's really find the dimensions. Let's find the dimensions with the largest surface area. Let me change this here. Find the dimensions with the maximum surface area. That might be the real question. Find the dimensions. With maximum surface area? It's kind of a weird question. No, this is really bothering me. So 1200 centimeters of material. Something's really bothering me about this one. Well, let's see our equations here. It should be the other way around. So I think this is worded wrong, but I'm gonna. Man, this is not a good day. 1,200 centimeters of material is used to make a box with a square base and an open top. Find the dimensions with the maximum volume, maybe. Let me see if I can. If I don't find it in the book somewhere. I might have messed it all up, but it's okay. Might have messed this one up. This looks like it makes a little more sense to me. 1,200 centimeters of material, that's area, is used to make a box with a square base and an open top. Find the dimensions of the maximum volume. So here's what. So now this makes a lot more sense to me. However, let's see. We might have gotten ourselves into some trouble if I changed it the way we did. I'll have to find the original question, but 1,200. So let's see what that means. 1,200 is 2s squared plus 4sh. We got to maximize the volume, right? And so your volume is here. And let's see. Let's hope we don't really mess it up. 1,200 minus 2s squared over 4s equals that h. Is that true if you solve for h? Right? Because you might say, why is this an issue to maximize the volume? Because volume is now a function of s and h, two variables. You need to create a one variable. So using this, I hope it's not screwed up. Let's see. S squared, what is h? 1,200 minus what? 2s squared over 4s. So that my volume will be S. S over what? 1200 over 4. Just an S over 2S. Or my volume's going to be 300S minus 2S what? Squared. Double check, ladies and gentlemen. Okay, double check my arithmetic's okay. There we go. I'll have to double check. 300S, because we simplified here, we canceled the S. So it's really S over 4, so it'll be 300S. Yeah. 2/4. Nope. Let me double check my arithmetic. Let me not get fancy. Okay, I'm going to do it this way. I think that's an S cube. Yep, that's S cube. Okay, let's not get so fancy. So this will be what? 1200 S squared minus 2S to the 4th over 4S. Now that'll be what? 300S minus, is that 1/2 S cube? Double check now. Yeah. So we're going to have to maximize the volume here. Vmax. Okay. Let's do some calculus. Take the derivative with respect to S. Your 300S minus 1/2 S cube, which gives us what? 300 minus 3/2 S squared, okay? Set that equal to 0. So 3/2 S squared, 300 minus 3/2 S squared equals 0, which will be 3/2 S squared equals 300, right? Or S squared will be 300 times 2/3. S squared is going to be 200, I believe. 600 divided by 3. Okay, so S is plus or minus the square root of what? 200, or it's the positive answer. So your S will be 2, it looks like 10 square root of 2. All right. So this is supposed to be the side that probably maximizes this equation for volume. This is my derivative. Okay, so by sign analysis again, we're going to get that side here. 10 square root of 2, this is the side that makes this what? And then you're going to have to use 0. Do you guys happen to know what is 10 times the square root of 2? Yeah, I don't know. It's 1.4. It's about 14. So I'm going to say, yeah, let's set SB 5 as a test point. And maybe 15 as a test point. Or maybe to be safe, 20. Okay. Okay, so plug in 5 here. 300. Here's your test point. 5 goes here. Isn't that 25? 75 halves. It looks like this is going to be what? Positive. Okay, double check. 20 now. Ooh, that's a pretty big. 20 squared. Looks like that's going to be negative. Okay. So sure enough, you're standing on top of a what? Of a hill. That means that is a maximum. There's a relative max there. So that makes sense. Okay. So relative max for what function? For v. So v max is f, or whatever that was, of what? 10 squared root of 2. That's the side s. V max happens for the original function v. Right? You have a relative max there at 10 squared root of 2. So that's the side, and they're going to want that. So this is 10 squared root of 2. Here's my point. So the sides have to be what? That's squared. Now, what is h? Right? You might say, okay, that's great. We have the sides, but what's h? Because they want the dimensions of the box, really. So h you can get easily if I go back here. Right? Here's my h now. So you plug in, you might be able to go back here instead. Remember the volume, well, where is it? Oh, here's h, sorry. So you're going to have to plug in that 10 squared root of 2. Oops. And isn't 10 squared root of 2 200? I think that's 200, right? So let's see what the height has to be of this box. You're maximizing the dimensions. So the height of that box, 1200 minus 2 times, I believe that's really 200, over 4 times 10 squared root of 2. 1200 minus 400 over 40 square root of 2. So your height's going to be 800 over 40 square root of 2. Isn't that 2? Right? 800 divided by 40. What is that going to be? 20? 20 square root of 2. So you can rationalize. So it looks like the height of the box will be 20 square root of 2 over 2. Oh, look, sure enough. What's this? Oh. It's the same dimensions. 10 squared root of 2. So, ladies and gentlemen, you found the dimensions here for the sides and the height. It's going to be a square box. That sounds about right. Same kind of scenario. It's analogous, square box. You say, why is it square? Because your sides, here's the conclusion. The side equals the height, which equals 10 square root of 2. So, ladies and gentlemen, I took these notes from I don't know when, and now that makes a lot more sense because they're giving you the surface area of material. That's how you buy material, surface area. And they want to maximize the volume. And this box doesn't even have a lid. So this is another very, very classic optimization question that we started. At least we got 3 in. We'll do a couple of more maybe tomorrow, but if you said you would like to see more examples, where are they? Yeah, I got some more examples just so you guys can see. Look at this function, right? I did this. Here's a point closest to the origin. Oh, again, you're going to see the same distance formula. D squared. You go, oh, here's another point. What? 3, 0. Closest to the origin. You're going to see another D squared again. Oh, this is kind of like we did today. Example 3. Classic fundamental bread and butter questions. Bread and butter. And then this is one we could try to do tomorrow. This is another classic one. Find the dimensions of the largest rectangle that can be inscribed in a semicircle of radius 1. It's in the book, or it's in the video. And then find the dimensions of the largest rectangle that can be inscribed in a unit circle. Does that even look like a circle? Looks like an ellipse to me. I don't know. Oh yeah, it does look. No, does it? Is that a circle? Maybe. And find the area of the largest rectangle that can be inscribed in an ellipse. So 5 and 6 are similar. One's a unit circle. X squared plus y squared is 1. And then the ellipse has, the equation ellipse. So maybe we'll do a couple of these tomorrow. What do you guys think? All right, you guys. I'll put some homework. I think I'll try to find homework on this that are similar questions. But I just wanted to go over some of the classic kind of questions. Just reading this last one, it didn't make sense to me. So now it makes sense. But box with a square base, open top. Well, there's different versions. I think I did. I don't know. I'm just going to look at some other. Yeah, I know what I did. Anyway. Okay, we'll see some more examples tomorrow. We'll see you guys later. Take care and stay safe. You guys know what I mean? You say, what do you mean go with the formula? Well, there's a lot of things that we have. I think we're talking about optimization. So you have additional examples here, right? So I would say to you guys, look over the additional examples. Did the additional examples help you in the past, you guys think? Yes. Anybody? See, resources are only as good as the people that use them. Meaning if you don't use them, they're not any good. But if you used them, those who have, did you find it helpful? Yeah. And that's the idea. So here's another example of, some of this optimization, questions. We did have a little rough day yesterday, had no sleep, but I had some sleep today. So hopefully it'll be better. But we found the errors, and that's all that matters. Okay? So you got additional examples there. So what I want to do is not go exactly over these additional examples. We'll give you some more examples. I'm looking at some of that stuff there. Yeah, okay. So let's go over an example that I just found out of your book, and I'll put this here. I like this example because it's kind of related to some that we've done. So this, again, is under optimization. And if you ever think optimization, you're just actually finding the relative max or relative min for a single variable. In all honesty, you go, what are you talking about? Well, all right, now let's read this one, right? What does it say? Find the points on the ellipse that are farthest away from the point 1, 0. That happens to also be on the ellipse, because when I read my notes, I don't really have, when I take notes that I write things down at times, I write them down to myself, hey, go over that question, do this, do that, blah, 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 right? So, I don't even have it all worked out at times. So just let you guys know. So some of my notes are like, okay. So here's one. I said, wait a minute, here's a point on the ellipse. I thought it would be like off the ellipse, but it's not. Okay. And so they're saying find a point on the ellipse. Here's the ellipse. If I said to you guys see this particular point, by the way? It's represented by arbitrary xy. Well, that point from the point 1, 0, that's a certain distance away. Is that right? That's a distance. In fact, every point has a particular what? Distance d. Away. And those distances are, for the most part, different, I guess. Okay? So you have a lot of what? Points on that curve where you have a fixed distance away from the point 1, 0. And the question is, they want you to find the what? They want to, the point, remember the point is a location. It's an x and y coordinate. Okay, so they want you to find an x and y coordinate value. So I'm just kind of looking over what I have here over the years, and I don't even know the answer. That's farthest away. And you go, what do you mean farthest away? Well, the maximum distance. So farthest away actually means D what? Max. You guys with me on that? So there's no coincidence, again, that this distance formula rears its head. Just like an example that we did yesterday. We did a minimum distance yesterday. Now we're going to do a maximum distance. All right? You guys with me on that? You guys see what my point to you guys on this? All right. Now that's the curve here. So now, ladies and gentlemen, you're going to use that distance formula again, right? Where the distance formula is that x2 minus x1 squared plus that y2 minus y1 squared, just like yesterday. Okay? Because you're going to try to maximize that D. This is optimization. Right? That's the idea behind optimization. That word can be pretty deceiving. All it is find relative max or relative min, depending on the question. So, like I said yesterday, there's a couple of things you can do. Maybe we'll do it. Start a little different. Yesterday, to get rid of that square root, we said square both sides, and so I get d squared now going to be what? Everything you guys see here. Okay, so you're going to see that there. Now, we're going to have to get a grip on what everything is. Like, for example, if I said to you, it looks like, to me, really a point that might be farthest, maybe something like this, somewhere maybe, I don't know, over here, I guess. Okay, you guys see what I'm saying? That might be, to me, something like that. Maybe this other point is farthest. I don't have to do that. But I just want to share with you guys my thought process. And they gave me a point 1, 0. So I'm going to call this point 1 and this point what? 2. Okay, you guys okay with that? And so point 2 is an arbitrary x and y. Point 1 is 1, 0. So when I go back and plug this in, I'm going to get now the d squared going to be what? An arbitrary x minus 1 squared plus an arbitrary y minus, looks like 0 squared there. Is that right? Because that's the y coordinate. X and y. You with me on that? Distance formula. So you're trying to get this these 2 points here. Okay? Something like that. But you guys notice something here that might be an issue. Maybe not. Let's do a little bit of algebra here, okay? So that d squared is x minus 1 squared plus y squared. This d squared is a function of x and y, 2 variables. You need this to be a function of 1 variable. This is the idea behind optimization. This is calculus of 1 variable. So you might say, how do you get the y how do I get that y variable, right? Well, you got to go back to the equation. And what's nice about this ellipse is that you don't have to solve for y and square it. You can solve for y squared, and that's now 4 minus what? 4x squared. So for this, we can replace that with a 4 minus what? 4x squared. So ladies and gentlemen, that d squared is x minus 1 squared plus 4 minus 4x squared. Let's not make another typo and go get that coffee. Let's double check. 4 minus 4x squared. Okay. So at this point, let's actually be clear here. This is not D, this is D squared. So you say, I kind of have an issue with that. And I'll tell you, don't worry. If you want, call this f of x, because this is a function of what variable now? This is a single variable x. So what you're going to end up doing is not optimizing D, because we're going to have to now optimize f. We got rid of the square root. Now, if you're stubborn, you may say, I'm going to do this by keeping the square root because I like that idea with D, optimizing D, because I want to get D max. Well, D, you can do that, but the algebra and the calculus would be more difficult. So square the D, and now you get rid of the radical, and you can still do the question with D squared as opposed to D, because there's that relationship between a number and squaring it. It's kind of like if you guys took statistics, variance and standard deviations are really a measure of consistency. One's the square of the other, though. And you have to find a variance, because to do processes in statistics, it's easier to get rid of the radical. And that's going beyond the scope, but that's kind of exactly what happened here. Get rid of the radical. Call that D squared, and then I just named it F. So you're really optimizing this. This is now calculus, relative max, relative min. And that's it. And that's what they mean by optimize, the relative max, relative min idea. So in my mind, whenever I see optimization, I just think, oh, relative max or relative min. You can't find both in optimization. It's either going to be one or the other. It's going to have a relative max or a relative min. In this case, it's going to have a relative max because they're asking you for maximum value. There won't be a relative min. So just kind of throw that out there that you guys are aware of the feel of this topic. And then now it's like, okay, everything you've ever done in the past, you guys took a test on this. It's a nice polynomial, right? Polynomials are nice. Which ones are not nice? Square root? Trig functions? I would say trig. I think trig functions are nice personally. But you got to have a good trig experience. If you don't have a good trig experience, you're scared about trig. I mean, that's the truth. And you say, how do I know that? Because you guys, can I tell you a little secret? Just don't tell anybody. I'll tell you a secret. I'm going to tell you guys. Because I don't have the energy to lie. I've lost my whatever it is. When I took calculus, I actually took a trig course before. And I got an A. In fact, the whole class got an A. And that was an ELAC here. And I took it at night and I got an A. And you want to know what happened? Well, I showed up just like the whole class. And the instructor who taught trig, he lost his marbles. He was done. I don't know what happened to the guy. He was a nice guy. But he lost his marbles. So we'd come in every day to our trig class. It was a night class. And Mr. Snodgrass, whoever that was, I can't remember his name. He was standing at the podium. The lights are off without a projector. What's going on here? Lights are off. No projector even. I mean, our lights are off because we have a projector you guys want to see. There's a reason. There was no reason for the lights to be off. So he'd stand up at the podium, and he had the trig book, and all he did the whole hour was scratch his head reading it. Like, what's going on? And we're all looking at each other. What do we do? What's going on? He forgot trig. He lost his marbles. And he just couldn't make sense about anything that he was doing. And we just asked, hey, Mr. Snodgrass, do you mind if we read our book? He said, sure, okay, read your book. So I didn't learn trig from him. You know what I had to do? Read the book and learn it myself. Now, some of you guys can look at that and you say, hey, that's a horrible experience. And it is a horrible experience because I resented it. I wish I knew trig. Because that meant I now had to go back and read it all on my own, study it on my own, review it on my own, and now I teach it. But I had to learn it on my own. That's what you did. I had to read. So those things never go away. You're going to have to review. So it's ironic. Sometimes I think about that and I go, was it the best experience I ever had or the worst? It's both. Because it forced me to have to become a student. And those skills that I learned about reading were skills that helped me throughout my whole student experience. I had to behave now like a real student. And that was the interesting part. So it wasn't a curse, it was also a blessing. You see my point? So now, so some people are like, I don't know trig, Mr. Judge. I don't like trig. Well, go back and what? Read it, review it. Get used to it, because that's what you're going to do your whole college career. You're going to review. You got to do it. It's the way it works. But I do wish at least I didn't have to, if I had a good solid trig foundation, things probably would have been a lot smoother for me. Maybe I would have time to do a little extra, something different for a while, right? Give you less time. So, that's kind of my advice, just to kind of remind you guys, it's kind of ironic. Oh, we got a like. Oh, wait, who's out there? Is that? We don't even know. I say good morning and that nobody ever responds. They're probably in their slippers. Do you guys know what I mean? Interesting. Okay, well, that's fine. Just be careful. Sometimes that comfort is what? Is the worst. How about this? Do you guys know? You guys know how to do this, right? Do we have to go through every step? You guys know how to get a derivative. This is 2, what? X minus 1 times 1. Don't forget chain rule. Minus 8x. 2x minus 2, I think. Minus 8x. And then this will be negative 6x minus 2, looks like. All right. This is my derivative. Good job. So you go through the process. You go, oh, I got to find those critical values. Yes, set the derivative equal to 0. And what that means is we get negative 6x minus 2 equals 0. And that means minus 6x equals positive 2. And that means x is negative 1/3. You guys okay with that? All right. Now, so that's kind of the x coordinate. But, go back and take a look. What's the domain here, ladies and gentlemen? I'm going to get rid of all the drama there. Right? You see these x values? These x values have to be between what? Yeah, I'm going to try to find something between negative 1 and 1. Is that right? So you might say to me, why do we always go back and look at this and say this is the domain, right? Because you got to put this in context when you do your sign analysis. If you don't, you go about it really what? Problematic. Is that negative 1/3 between those two numbers? Here's what I'm saying. This is the domain for x, right? And you found a critical value. The critical value is at negative 1/3, where that derivative is 0. So you have region 1, you have region 2. There's your derivative. All right, you guys okay with that? So what do you do with the sign analysis? You need a what? You need a test point in each region, right? So I like 0. Is 0 available? Sure is. And then what's between negative 1 and negative 1/3? Maybe negative 2/3? So, okay, we're going to have to test the what? These are our test points. We got to test the first derivative, and the first derivative is right here. You might be able to. Is it on the curve? I think so. You might be able to. Maybe you can make it easier than that. So if we use -1, what's the deal? -6 times -1 is +6. Is that right? +6 minus 2 is positive. Is it going to be 6 minus 2? Is that 4? So you're going to find what? Region 1 is positive. If you use 0, what do you find about region 2? And so, ladies and gentlemen, take a look. This is increasing, and this is what? So sure enough, you're standing there on top of a hill. This is the location of your relative what? And there is no what? See what I'm saying? Just to kind of throw that out there, because sometimes people look at this and they go, hey, Mr. Judge, where's the relative min? There is not going to be one in that context. There's no valley. So they're not going to say, hey, where's the minimum distance? Sometimes people want to know that. They go, hey, how come they're not going to change that and say, what's the minimum distance? Because it's not part of the process. You know, the minimum distance will be the point itself. It's trivial now, right? So it's going to happen at x is -1/3. But then the question is now, what is y? So if I know x is -1/3, what is the y coordinate going to be now? Anybody have an idea? How do you get the y coordinate?
You substitute back to the original.
Go back to the original question. Copy. So we found x. Okay. So you say, what's my y? Should we close the door? Let's close the door. I get scared sometimes. I get frightened easily. X is -1/3. So I get 4 -1/3 squared. Y squared is 4. 4/9 plus y squared is 4. Y squared will be 4 minus what? 4/9, okay? And I guess let's just do a little bit of arithmetic, not much. 9 times 9, and your y squared will be, looks like it's 36. 36 over 9, looks like -4/9. Double check. And it looks like that'll be 32 over what? 9. So y becomes plus or minus square root 32 over 9. Y will be plus or minus. You guys can simplify that square root of 32, right? And that's over 3, by the way. 16 times 2, is that right? That'll be 4 square root of 2 over 3. Now, what am I saying about this here? You guys notice anything about this? There's actually what? 2 y values. There's 2 points. So the x and y coordinate, you're going to say -1/3 positive 4 with 4 square root of 2 over 3, and -1/3 -4 square root of 2 over 3 here. Okay, so let's move this to the center. And here's my 2 locations, and this is, again, sign analysis on the first derivative, finding a relative max. And let's go back, if we can, 4 square root of 2 over 3. I'm going to go back to Desmos here, okay? So -1 divided by 3, comma, 4 square root of 2 divided by 3. I'm going to label that point. And then, again, -1 divided by 3, comma, -4, where are you? Square root of 2 divided by 3. We're going to label that one too. Now, I'm going to change the colors just to match. A little bit of OCD. Not really. You guys see what I mean? You're going to find those locations in the same color. Anyway. And so, ladies and gentlemen, if we look at this here, it kind of makes a little sense that there's actually what? 2 locations because of the strategicness of the point that they gave us, right? These are the address because they wanted you to find the distance where they have maximum, we have maximum distance. And if they really got creative, you say, oh my God. No. What is the maximum what? Distance. D. Okay, there's actually 2 locations. So you might even say, what is that maximum distance? How would you find it? Just take one of these points and plug it in your distance formula. You just have to use the what? Use the distance formula. And you can call that your second point. What was that first point? Right? So this is your first point, and this is a what? Any one of these points. It doesn't matter. Okay, because it's the same. It's going to be the same distance. There's some symmetry there. Some nice symmetry. So if they want you to get the distance, you just do that. I think that's what? Negative 1/3 minus 1 squared plus 4 square root of 2 over 3 minus 0 what? Squared. Double check. Is that true? 16/9 plus what? 32/9? Double check. I'm not awake. (48/9) Square root of 48, we can simplify that. Square root of 9, we know what that is. 16 times 3, is that true? It's 48? So your distance will be 4 square root of 3 over 3, I believe. Double check. Let me double check that. Sometimes when you talk, write, and think at the same time, it's easy to make arithmetic errors. Square root of 16 is 4. Square root of 3. 16 times 3 is 48. 4 square root of 3 over 3. Okay, that's actually the maximum distance.
I have a question.
Yeah.
So you just choose a value, right? Whether it is positive or negative.
Oh, you're right. Because you know what's going to happen for the x coordinate. Well, yeah. Well, what's going to happen for the y coordinate? You're going to square it. So you got plus or minus here. What happens when you square that? Right? It's going to be the same answer, just so you guys know.
So negative or positive doesn't really matter.
It's not going to matter for a couple of reasons. there's symmetry here, so that distance d will be the same value. But algebraically or numerically, you go, oh my God, you got 4 square root of 2 minus 4 square root of 2. What happens when you square that right in here? Isn't that still going to be 32 over 9? 16 times 2 is 32 over 9, yeah. So it won't matter. So sometimes you're looking back at the book, they'll do that plus or minus and it'll get squared. And that's the distance. Just kind of throw that out to you guys. So you see the difference between what they're asking. They're not asking the maximum distance. They're saying find the what? Points on the ellipse, on the curve. Anyway. Optimization question. I thought it was a beautiful question when I looked over my notes. I don't even have the answers. So I just remembered, hey, let's do a couple of these. And I'm going to do another variation. And I'm going to create the question. Find the dimensions of the rectangle. It's another kind of classic question. Find the dimensions of the rectangle with the largest area. That can be inscribed in a circle of, I'll say, radius 4. Okay, I'm kind of making it up. So I want you guys to note when they say this, they didn't say where it was centered, but it's going to be centered at the origin because the equation of your circle centered at the origin is x squared plus y squared equals 4, okay? They didn't say anything about the center of the circle, but that's what they mean. And I'm going to go to Desmos. Okay, I'm going to do a unit circle, x squared. Hey, where's our plus? Is there equal down here? What happened to the keyboard? Oh, there we go. Equals 4. Okay, let's change the color. Well, we'll keep it this way. All right. All right, so here's your circle, and then what do they say? Find the dimensions of the rectangle. So, I guess, I don't know. Can I draw? Let's do it this way. All right, find the dimensions of the rectangle with the largest area. All right, now I'm going to do this here. Start by, ladies and gentlemen, take your arbitrary point on the curve. All right, so find the dimensions of the rectangle with the largest area. I suspect it may not even be a rectangle, but we still need to get the dimensions, okay? Now, the dimensions, the largest area of a rectangle. So what is the area of a rectangle? Do you guys know? It's length times width. So when they say find the dimensions of the rectangle with the largest area, I see that and I go, A what? A max. Maximize the area. So, okay. Are they talking about this function? Yes. Maximize A. So we got to have a length and a width. It has to be a point on that curve. Tell me if you guys agree with this. Can I say my area here is 2x times 2y? Can I say that? Why can I say that? Length, what? Width. You guys okay with that? So if I label this point, that means this distance is what? X. Is that true? And this distance is what? X. This is hence, well, if that's the width, well, I'll just do this. Length, width, doesn't matter, okay? So then that's where I got my what? 2x. You say, how do we get 2y? Well, this distance will be y, and this distance will be y, and that's how you get 2y. So your area is really 4 what? 4xy. Now, what's the problem again? Is that your area is a function of two variables, x and y. So we need that to be a function of a single variable. This is calculus of one variable. You got two variables. So you might say, well, how do we change one of the variables to like the other, right? How do we change y to x or x to y? You go back here. What's your formula? What's the equation of the circle? Isn't it x squared plus y squared is 4? So I might be interested now in doing this and solving for y. So this means y squared will be 4 minus x squared. And then you got a problem here, ladies and gentlemen, because your area formula doesn't have a y squared. It has just a y. So you might say, well, what does that even mean? Well, that means y is plus or minus square root 4 minus x squared. Okay? And then you say, well, what does that mean? Well, which one do you use? The plus or minus? Why use plus? Well, remember, y can be both positive and negative. This is on our Cartesian coordinate system. But if we use the y being what? Positive, that's the upper half of that circle. Just so you guys know. So then your area formula will be the following. Area will be, well, what is that, 4x? Times the square root of 4 minus what? X squared. And then this is good for what? What is your x values between? -2 and what? +2. These are the x coordinate values. These are the y coordinate values. So we already know the domain of this function will be between -2 and +2. And we'll just keep that in blue. Well, we'll do black, 4x. Yeah. Oh, radius is 2. No, what do they say? Let's do it. Radius is, let's fix it. Thank you. Radius is 2, sorry. 2 squared, 4. I don't want to change everything. So area is going to be what? 4x square root 4 minus x squared. I'm glad you guys caught that. The formula is still correct. You guys know why? Because it's x squared plus y squared equals what? R squared. So if your radius is what? 2 squared is what? 4. So good. Now it's consistent. And you can actually see the radius is 2 here, by the way. Okay? Just so you guys can see that distance, all this distance is 2. That's your radius. Okay. So we're good. We don't want to change that stuff. We did all this work. So here you guys go. What do you do with this now? You maximize. You optimize. And you say, what in the world is optimization anyway? Find your relative what? Max. Relative what? It's going to be a relative max. You're going to get a maximum area. And they're asking for dimensions. They didn't ask for the area. Anyway. So, as you guys know, and you can call this is an area formula. You can call that A of x. So that A prime of x is the derivative here. Okay, what do you guys know? You say, oh my lord, they gave me the product rule. Is that right? You got product rule. All right, so product rule and then product rule of chain rule. So you get 4x, the derivative of 4 minus x squared to the 1/2 plus 4 minus x squared to the 1/2 derivative of 4x. Let's find that derivative. And this here, okay, let me see if we have space. That's going to be 4 minus x squared, well, 1/2, right? To the minus 1/2 times negative 2x. And this derivative is nice. That's only going to be 4. Okay. So let's see what this becomes. I'm going to get rid of my 2's now. Okay, I got the 4x here. I'm going to be careful. Negative x over square root 4 minus x squared plus 4 square root 4 minus x squared, okay? Let's double check. 4x minus x all right, now we're going to have to simplify. What I mean by that, we're going to have to add right here, okay? So adding right here, let me change the color. We're going to do some arithmetic. So you guys know the detail there, right? So this will be what? Negative x over the square root 4 minus x squared plus 4 square root 4 minus x squared square root 4 minus x squared over that square root 4 minus x squared. You guys agree with that? You guys know what I'm doing? Yeah. Well, I'm going to do it at the end. Oh, oh, you're saying, oh, good observation. Jeez, that's 2. Let me see. Let's double check. Okay, good observation. All right. Let's do it now. That's going to be minus 4x squared. Okay. Let me double check here. Okay, 4x. 2's go away. X minus 4x squared. All right. So it's all going to be here then. Okay, so now that's good. So then now, ladies and gentlemen, here we go. Negative 4x squared divided by square root 4 minus x squared. This will be plus what? 4. 4 minus x squared over that square root of what? 4 minus x squared. So now, ladies and gentlemen, what do we end up with here? Is that negative 4x squared plus 16, bless you, minus 4x squared over your what? Square root of 4 minus x squared. So you're going to have now 16 minus what? 8x squared over square root 4 minus x squared. So that kind of looks okay. Does that look okay? Let's double check. So you guys can see that here. 16. Yeah, that's going to be r squared. All right. Does that look okay to you guys? Double check. So with this derivative, we got to be careful here, okay? When you use your sign analysis, let's go back. What's the domain here? From negative 2 to what? To positive 2, is that right? So I want you guys to remember this is from negative 2 to positive 2. And this is on the first derivative, so this is a prime x. Now, what am I going to say here? I'm going to say at negative 2 and positive 2, what do we know? The first derivative does not exist. Does anybody know why? Don't you set the denominator equal to 0? So if that square root of 4 minus x squared is 0, what that means is 4 minus x squared is 0. It means x is plus or minus 2. That derivative does not exist there. But what about the numerator? Right? What do you get here? (16) minus 8x squared is 0. 8x squared is 16. X squared is going to be what? 2. So what is x? Plus or minus square root of 2. So that derivative is what? 0. Region 1, region 2, region what? 3. So you guys are going to need some test points. What's available? 0. Okay, and what's bigger than the square root of 2? Isn't that 1.5 maybe? 3 halves? Use maybe 1.7. Maybe minus 1.7. Test points. So double check, ladies and gentlemen, see if we're okay with this. Does that look okay with you guys? Okay, now check here. 0, if we plug in 0 there for that test point, what do you guys get? Don't you get what? Is that positive? What if I plug in 1.7? What's 16 minus 8 times 1.7? Do you guys know? Should we wake up the TI calculator? We can't plug in 2, can we? It's not like the last question. So 16 minus what? 8 times 1.7 squared. Okay, so those people at home, you go, what are you doing? 16, is that right? 16 minus 8 times 1.7 squared. Oh, that's negative. Okay. So, and it doesn't matter if what? That test statistic is positive or negative because you're going to square it. You're going to square it for x squared here. The denominator is going to be fine. So, decreasing already. So, where do you have a max, a relative max? You're on top of the hill where? Right here, is that true? So your area, here's your conclusion, has a what? A max happens where? At x equals what? The square root of 2. However, what's your answer? You guys remember? What's the answer? Go back over here. Find the what? What's the dimensions? It's the length and width. So if you're awake, what they're saying is this location is the square root of 2. What's the length going to be then? Wasn't that the length and this is the width? So your length will be 2 square root of what? X. Is that true? You just found the length. How do you get the width? How do you get the width? How do you get y? 2y is the width, isn't it? So how do I get y? Go back over here. I'm going to erase this. You guys, can I do that? So you say, how do I get my y value? Well, what was the x value? What do we say x was? Is that the square root of 2? So y squared is 4 minus, what's the square root of 2? What's the square root of 2 squared? Isn't that 2? Y squared will be what? 2. Y is plus or minus the square root of 2. So you get that positive value, square root of 2 here for y, but what does that mean about the width? Your width is 2. Oops, square root of 2. Let's not square root of x, square root of 2. All right, here's your length. Here's your width. These are your dimensions. So it turns out yet again, ladies and gentlemen, what is that? What's the moral of the story? It's a square. Length will be 2 square root of 2, and width will be 2 square root of 2. So again, that's the moral of the story. Now, that doesn't tell you what the maximum area is. You can get the maximum area, but this is the dimensions of that particular rectangle, which is not really a rectangle. It's a what? Square. And if you said, what is the A max, by the way? Well, do your multiplication. 2, what's the length? 2 square root of 2. What's the width? 2 square root of 2. A max will be 4 times 2, which is what? 8. So double check if my arithmetic is okay. I'm not awake. 8 units squared. So again, it turns out to be that nice what? Square situation. And so, ladies and gentlemen, I'm going to do what now? I'm going to pass back your test. Okay? You guys good with that? What do you guys think? Isn't that a kind of a nice question? Those are nice. Yeah.
For the x and y values, is it just like the value that we kind of make it up?
No, these are values on the curve. We didn't make up those values. These are points on that. It's not a unit circle, it's a circle of radius 2. So it's a point on that curve that you can inscribe, meaning draw inside that circle. They want to know the dimensions. It's a classic optimization question.
Oh, so we just like 4 times the square, like, so we have 4 squared, right? So that is why we like use 4 times x.
Well, you have a lot of squares, but they're talking about that red square there.
Yeah.
They're talking about the dimensions, length and width, and it's on your Cartesian coordinate there.
Okay.
So it's x, y. So I just wanted to kind of show you. They could change the radius on you. It could be radius 1. They use a unit circle. They sometimes give you that question in terms of a general radius r. And you go, how do I deal with r? R is a constant, you know. So when you differentiate, you know, you think of it as a constant. So your book will actually use r. I throw some examples here with numbers so you can see the calculus. And there's, of course, other examples on my website there, too. So, ladies and gentlemen, let's pass back your exam. Okay? When's your take-home portion due? Monday. Good. Okay. Some people already turned it in, by the way.